Um, so I'm at Texas A&M University working with Professor Ibrahim Karaman. And again, my thesis is about iron-based shape memory alloys, and I will be talking about today how can we incorporate this iron-based shape memory alloys in structures. All right, so every year, okay. All right. Can you hear me? Perfect. So we know every year the frequency of the disaster increases, right? We see more and more hurricanes and disasters, and it is extremely critical to detect the failure before this catastrophic failure happens in the structures. To improve, of course, we need to identify the defects to improve the performance of these structures. To do that, we need next generation structures with health monitoring systems. One way is to do that to integrate high performance materials and systems into the structures. This can be achieved by using a shape memory alloy. So these shape memory alloys are a special class of alloys where they can recover huge amount of stress compared to conventional stainless steel alloys. So these materials go to a solid-to-solid phase transformation. Here, this is a typical superelastic shape memory alloy. They go to a solid-to-solid phase transformation from austenite to martensite, and this phase transformation can be triggered by stress. When it's triggered by stress, we call this superelasticity. And we can get up to 7 to 8% recoverable deformation from shape memory alloys, which will allow us to use this material as a recentering structures in the civil engineering area. For example, imagine during a hurricane, a traffic sign, usually we see lots of pictures where the traffic signs are collapsed, right? But if you do, let's say if you do use a shape memory alloy, you can still recover the deformation up to 7 to 8%. So they are very advantageous in that sense. And sorry. And I also brought some, this was in our showcase, but I brought 2 cables. So this one is a stainless steel cable that we know, so you can just deform it, right? But this doesn't recover back or doesn't remember its original shape. However, this is a nickel titanium cable where you can still bend very hard, but still it recovers its shape. So this is what we call shape memory or superelastic alloys. So most well-known superelastic or shape memory alloy is called nickel titanium. In other words, you can also hear as nitinol. Lots of people use this material, especially in the medical industry. However, they are very expensive, so they are not suitable for mass production civil engineering applications. And another disadvantage of nickel titanium is they are very compositional sensitive. So when you change the composition a little bit, the property of the material changes drastically. However, oops, sorry. However, iron-based shape memory alloys are much, much lower cost. So you can, that's why they are very suitable for civil engineering applications. They are very easy to process, so industry knows how to deal with them. They can process it very easily, up to 98%. You can do a cold work up to 98%. And they can provide theoretically higher transformation strain than nickel titanium alloys. So in our study, we choose a class of iron-based shape memory alloy called iron manganese aluminum nickel. So what's so special about this iron-based alloy is that the superelasticity, it shows a superelasticity in a large temperature window, and the properties of the material, they are not dependent on the temperature. For example, in this graph, this is a superelastic stress, which is a critical stress, where in this previous graph, so this stress, around this stress where you start to transform to martensite, this is what we call critical stress, versus temperature. And the red line represents iron-based shape memory alloy versus this line represents nickel titanium. So as you can see, if we change a 1 degree C, the critical stress of nickel titanium changes 6 megapascal. So this is a huge change. However, iron manganese aluminum nickel changes only 0.74 megapascal, which means that we can use this material without changing its properties over a wide temperature range. So in civil, you can use this in a cold temperatures or in very hot temperatures, and you will still get the same response. So, okay, how these materials work? So there are two things to get a full good superelastic response out of this iron manganese aluminum nickel superelastic alloy. These are nanoprecipitates and large grains. So what we need in this material is to have these nanoprecipitates. So what you want to do is, you can think of as you are trying to make a nanocomposite material. So you do some heat treatments and you induce these precipitates, and you can see if you don't have any precipitates in the microstructure, you get no superelasticity. So this material doesn't work. So in our group, what we realized that you can also change the critical stress by controlling the size of these precipitates. This is our work published at Scripta Materiale last year, that if you can change the heat treatment time, which you are changing the kinetics of the phases, you can alter this critical stress, and you can increase up to 600 megapascal. So it's not just doesn't just transform at the same stress. We can change this stress by changing the microstructure. And here you can see these nanoprecipitates here, and they show here the volume fraction. So this is rule number 1. So critical stress changes with nanoprecipitate size. Another very important thing to get a full recoverable superelastic response is to get large grains. So you need to have very large grains in this material to get a very good superelastic response. Here, these two graphs shows very clearly that, so this is a wire with a small grain size, response of a wire with a small grain size, and this is a response of a wire with a large grain size. So as we increase the grain size, we start to see superelasticity can recover deformation. Again, if your grain size is small, your material is not going to work. So second thing what we need is a coarse grain structure. Of course, in our group, we've done lots of studies to find out the ways to increase the grain size, and this looks complicated, but it's you can divide this into 2 processes, and it's more simple. We did this thermomechanical processing beforehand, and after, I'm not going to go into details, so after that you can get this huge grains, which I'm currently studying right now. And after you apply these processes, you get this very big grains with a very strong texture in 110. And good news is the scale up is possible. We are still working on it, but so this image shows a 0.5 millimeter wire. However, if you apply similar heat treatments, you need to change some things. You can still scale this up, this process, and induce these large grains in a large diameter wires. Again, this is, we are still studying on that. Okay, so now we know how our single wire works. How about the cables? Because in civil engineering, the elements are usually in the form of cables, so this is what we wanted to study. Therefore, we started our project to build a cable setup that will allow us to produce a different diameters of cables with different lengths. So this is our undergrad, Peter. He was helping with me to build this setup, and after he finished it, he was so happy, and I take a picture with the setup. So this is our cable setup, and he built this control system and designed it SolidWorks, of course, at the beginning. And as a result, we can now, in our lab, produce these cables, nickel, titanium, and stainless steel. It's 1 to 5, all right? Afterwards, we tested these cables, and you can see the results. Again, we designed the grips. For our projects, we also realized that, okay, because this is an iron-based shape memory alloy, it also changes its magnetization during transformation. So now this property is extremely important for us because that, as you can see here, as the stress strain changes, our magnetization changes, and we can detect this magnetization change using a sensor. And I'm skipping this because we don't have so much time. So now we know that iron-based shape memory alloys, we can recover large deformation. So it has recentering capabilities, and they can also show magnetization response, magnetization change during phase transformation. Now we are, okay, how can we use these two properties to solve a problem in civil engineering applications? Can we detect the cracks? Yes, because imagine if there is a crack in the structure, as this crack propagates, the stress state around that crack will change, right? And that will induce a transformation in iron-based shape memory alloy. And now that also changes its magnetization, which we can detect. So we are proposing a new halt monitoring framework in civil engineering that if we use the iron-based shape memory alloy, we can detect the cracks easily. And the most important things here is our load bearing and sensing elements are the same. And this is a collaborative project between Aerospace and Material Science Department. This is Dr. Karaman, and this is Professor Karaman and Professor Dr. Darren. And this is our industry person, Jeremy Sheffer. And here's our objective of our project. I will pass this because we don't have so much time. And thank you so much for your attention.